Welcome to my YouTube channel. In this playlist, we are discussing about the applications of operational amplifiers. In today's video, we are going to discuss about peak clipper circuits and how to design them using operational amplifiers. Let's start the video. So in this video, I'll be talking about peak clipper circuits and how to design them using operational amplifiers. Then how to analyze peak clipper circuits which are designed using operational amplifiers. Then I will briefly talk about a problem statement to design a peak clipper circuit to meet certain requirements. And by the end, I will show you a simulation of peak clipper circuit using operational amplifiers. So, the first question that comes to our mind is, what is a peak clipper circuit? So, peak clipper circuits are used to clip or restrict a voltage to a certain value. What does that mean? These restricted input voltages are basically a big issue for certain circuits or devices like analog to digital converters, because in these devices we have to limit the input voltage to a certain level. Otherwise, if we apply a higher voltage to the input of these devices, they might burn or they might damage the device. So generally, clipper circuits are designed using combination of diodes and resistors. But using diodes and resistors, it is very difficult to achieve precise limits of higher and lower voltage levels. These voltage levels are the clipping voltage level thresholds. So, peak clippers using operational amplifiers can be designed in such a way that we can meet very precise limit of output voltage levels. So, let us try to see how to analyze a peak clipper circuit using operational amplifier. For that, I am going to take a problem. So, the problem is to design a unity gain variable peak clipper circuit using operational amplifier. So, the important things to be noted here are the gain of the amplifier should be unity, that is equal to 1, and peak clipper circuit should be designed using operational amplifiers, and assume the upper and lower limits of the voltage are 6.3 volt and 4 volt respectively. So V max is 6.3 and V min is 4 volt. So to design such a circuit, we have to use the op-amp or operational amplifiers. Now the question is, to design such a circuit, how can we choose the values of different components which are used in the circuit? So let us start the analysis. So we know that the voltage max is provided in the question, 6.3 volt, and that should be equal to the breakdown of the Zener voltage. Here we are using Zener voltage back to back, and the forward voltage of the Zener diode. So Zener breakdown voltage plus Zener forward breakdown voltage, both we have to know. So first, to choose the correct value of Zener voltage, we can use this equation, Vz equal to V0 max minus Vf. We all know that forward breakdown voltage of any Zener diode voltage is 0.7 or more or less equal to 0.7. And from the question we know that the voltage max is 6.3 volt. So we need to choose a Zener diode with a breakdown voltage of 5.6 volts. So this is our first requirement. So we have to use a Zener which should be having a breakdown voltage of 5.6 volt. Now, assuming I1, here I1 is the current which we are assuming to enter into the operational amplifier. Though we say that the operational amplifier has ideally infinite input impedance, but we all know that the input impedance of operational amplifier cannot be infinity. For therefore, there is some very high input impedance which is present in the input terminals of the operational amplifiers, and looking at that, we can assume a very small current enters into the operational amplifier. So for 741, the value is 500 microamperes. So in roundabout, we can take the current to be 1 milliampere, because this is also a very small value. So we are assuming the current entering into the op amp is somewhere around 1 milliampere. Now to choose the value of R2, that the feedback resistance, we can use the equation R equal to V by I. So V naught minimum by I minimum. So V naught is given here 4 volt. So V naught minimum is 4 volt divided by 1 milliampere. We get resistance of 4 kilo ohm. So we can choose, or we can put a resistance R2 of 4 kilo ohm in the circuit. Then after that, to take a resistance or a variable resistance, because we have to vary the voltage between 6.3 to 4 volt, we have to choose a variable resistance also. For that, we can use this equation VR4 is equal to V max minus V min, or V output max minus V output minimum, and putting the appropriate values, we get the VR4 should be 2.3 volt. So voltage drop across the resistance R4 should be around 2.3 volts. So the value of R4 should be VR4 divided by I1, which is the current entering into the circuit. So that is equal to 2.3 volt divided by 1 milliampere, and we get the value of R4 somewhere around 2.3 kilo ohm. So we can choose an appropriate potential divider circuit or a variable resistor in place of R4, which should match somewhere around 2.3 kilo ohm. These are very precise values, although you might not be able to procure these values. So you can buy some potentiometer which may fall somewhere near 2.2 volts or 2.2 kilo ohm or 3.3 kilo ohm. Now coming to the values of R1. So R1 should be R1 plus R4. The resistance or sum of resistance R1 plus R4 should be equal to R2. Why? Because we are going to design a unity gain amplifier. So the sum of these two resistances should be equal to the feedback resistances. So R1 is equal to R2 minus R4. We have obtained the value of R2 and R4. Substituting those values, we can get R1 is equal to 1.7 kilo ohm. Now coming to the R3. R3 is substituted here or connected here so that we can precisely balance the input current which is entering into the pin number 2 and pin number 3. For that, we can use the equation R3 equal to parallel values of R1 plus R4 and R2 respectively. Substituting all these value, we can get R3 should be equal to 2 kilo ohm, and it should be connected to the ground via or through the non-inverting terminal of the op amp. Now let us talk about the simulation part and see all the minute details of this particular circuit. So first of all, I'll show you how we can find the Zener diode. So here I am using a Zener diode which is having a voltage breakdown or breakdown voltage of 5.6 volt. Okay. So I have here connected a voltage source of 12 volt, Zener diode, and then 1 kilo ohm, and then ground. So this Zener diode D6 is forward biased, whereas D3 is reverse biased. So let me simulate this design, and you can see here we are applying 12 volt at the input, and after the diode we are getting 11.2 volt, somewhere around 0.8 volts loss. So the diode D6 is having forward breakdown voltage of 0.8 volt, which is more or less near to the 0.7 volt in our problem statement. Coming to the reverse breakdown of the diode, so here we have 12 volt, then resistance, and then we have connected the diode D3 or the Zener diode D3 in reverse bias, and we can see the reverse breakdown voltage is 5.61 volt. So keeping these two values in mind, we can further simulate the behavior of diode. So in this circuit, what we are doing, in this circuit we are applying a sine wave of peak to peak 20 volts, because here it is 10 volt peak, so 20 volt peak to peak, and I have used a resistance of 2 kilo ohm. You can choose any other value also. So let us simulate this signal. So at the output, or in the junction between resistance and the Zener diode, we can see we are getting a behavior which is in the reverse breakdown voltage we are getting somewhere around 5.575 or 5.58 volt, which is somewhere around 5.6 volt, and in the forward biased case we are getting 746 millivolt, which is 0.7 volt. So in this way you can test your Zener diode's behavior. And coming down to the first circuit, in this circuit we are using Zener diode back to back, D1 and D2 are connected back to back. So in the first case, suppose we are applying a sine wave. If the input is positive sine, in that case D2 will be reverse biased and D1 will be forward biased. So you will get a voltage drop of Vf and Vz using D2 and D1, because D2 is reverse biased, so it will have the voltage breakdown voltage of the Zener, and D1, since it is in forward bias, you will get the forward breakdown voltage. So 5.6 plus 0.7. Okay, and here we are applying a sine wave of peak to peak 4 volt, and we can see the behavior of the signal. So here we are getting a signal which is clipped from both end, positive and negative simultaneously. So you can see here the positive voltage is reaching up to 6.25 voltage, which is somewhere around 6.3 volt, and in the negative also we are getting minus 6.25, which is again negative breakdown voltage of the diode. But in this case, using this circuit, we cannot vary the voltage, or we cannot clip the voltage to an upper and lower limit, and neither we can vary the voltage range. For that, we have to use the circuit which was shown in the presentation, and this is the circuit which was shown in the presentation. In this, I am applying an input sine wave of 10 volt peak, and I have connected all the components which were derived in the circuit. So let us see the behavior of the circuit. So when the resistance is maximum, that is 2.3 kilo ohm, we are getting the maximum value of the signal, which ranges from minus 6.2 to 7, somewhere around 6.3, to plus 6.2 to 8. We can say 6.3, more or less 6.3. So the resistance, when it is maximum, we are getting 6.3 volt, whereas if I vary the resistance, you can see the voltage slowly is clipped more and more and more, and when the signal is when the resistance reaches to 0 ohm, we can obtain the minimum value of the input signal, which is 4.017 volt and minus 4.015 volt, which is precisely equal to the lower limit of the clipping. So this is the circuit which we can design to generate a variable clipper circuit, and by varying the value of R4 we can precisely clip the input voltage from 4 volt, here you can see 4 volt to minus 4 volt, and if I increase the resistance to its maximum value, then it reaches to 6.23 volt to minus 6.23 volt. In this way we have designed a peak clipper circuit, a variable peak clipper circuit with a very precise values at the output of the op-amp. So with this I am ending the lecture. I hope you liked the video. If you have any doubts or any comments, please put your doubts, comments and suggestions in the comment section. If you have not subscribed the channel, then I would request you to please subscribe the channel, and I will be always thankful to get your comments and suggestions. Thank you and have a nice day.